finite group actions and, well, it's there, isn't it? In orbit. That's great.
Thanks. Very nice to be here then. Great weather. So I hope everybody can have a great afternoon. I'll try to stay on time here.
I think you've got 50 minutes, Ian.
50 minutes.
Yeah,
Okay.
yeah. I mean, it's and we're starting same as yeah.
Okay. I haven't thought about this project for quite a while, but topics in this meeting make me sort of think that there are continuations that we might be able to get into. So perhaps there will be future developments. Anyway, finite group actions on spheres. Obvious examples, orthogonal representations of finite groups. Let's look at the unit sphere and a representation, gives you lots of interesting examples. And sort of key definition for this talk is the rank of a finite group. So this is the largest elementary abelian P group that you can put inside the group. And you maximize over all the primes, dividing the order of the group. So that's the rank. And this is the question of about the talk about finite groups acting on spheres. Well, the most sort of general version of this would be to look at finite GCW complexes. That's X, which are homotopy equivalent to a sphere. So the G in the CW complex, of course, encodes the action. The X, of course, could have cells of lots of high dimensions. It's only going to be the homotopy type of a sphere, not. And I'm saying rank one isotropy. So isotropy in a group action, you take a point and look at the elements of the group which fix that point. So it's stabilizer. Isotropy group is the usual term. I'll say a bit about motivation, I guess, for this question in a couple of different installments. But anyway, I think there are three nice settings to look at group actions on spheres, and the nicest one in some ways are smooth G actions on closed manifolds, which are homotopy equivalent to spheres. So thinking about high dimensions, we're looking at homotopy spheres perhaps, or even the standard sphere, of course. But when you say smooth group actions, they don't necessarily have to be the linear ones. The orthogonal representation spheres are examples. Another setting, though, is something called G homotopy representations. I'll explain this, give the definition a little bit more later, but essentially what these are GCW complexes, finite GCW complexes. And not only are they homotopy equivalent to some particular sphere Sn itself, but for every subgroup, the fixed set is also homotopy equivalent to a sphere of some lower dimension. So that's a concept introduced by Tom Dieck to sort of model representation theory in a more general setting. And the most general setting is the one that's in the question, that is simply finite GCW complexes homotopy equivalent to the N sphere. Okay, so those are the three settings. And in the talk, so this is all what the results I'm going to talk about are joint work with Ergun Yalcin, whose name will appear here later, and also Semra Pamuk. And our results at this stage are mostly, they're on problems B and C, or settings B and C. There's a third step, which is what you might call the surgery step, equivariant surgery step, to go from the results we have so far to understanding more of the first setting. Okay, so just some facts about groups acting on spheres. There's the classic P.A. Smith theory, and that tells you that if you have a group, so well, I guess I wanted to say that the assumption in the question was we were looking at isotropy of rank 1, and a little argument with Smith theory tells you that the group itself must have rank less or equal to 2. So this whole talk is going to be about finite groups of rank 2.
Sorry, forgive my ignorance. Are PA, are they initials, or do they stand for something?
That's P.A. Smith.
Right. Yeah. Okay. That answers my question. Thanks.
So this is the sort of classic foundational work from the 1940s on the beginning of transformation groups.
Right. He was still at Columbia when I was there.
But this work from 1940.
Yeah.
You met him? I never met him.
Yeah. No, he had the.
Oh, yeah.
When Thurston was proving the, whatever that was. That was the Smith conjecture. They were proving about knots, fixed point sets of knots being on fixed point sets of cyclic actions being unknotted or something. Yeah, he was there. He went to that.
A. Smith theory in its original form tells you that if you have a group acting freely on a sphere, say just or a finite GCW complex on which is a free GCW complex, then the group has to have rank less or equal to 1. So to get to rank 2, we allow this isotropy. Okay, so if you think about various kinds of groups of rank 2, there's the P groups, finite P groups. And there's a nice result from time ago from what's on the Hamrick that says that they all have, they all admit representations with rank 1 isotropy. Well, that's representation theory. And there's a formula in the Borel formula. You know, there's this marvelous book with the Borel Seminar on Transformation Groups, which is from 1960, I think. Which has lots of foundational work on transformation groups. Anyway, there's a nice formula. The point of this formula is that if your group is ZP cross ZP, the most elementary, if you like, rank 2 finite group, then you can predict the order of the fixed set from knowing you can pick the dimension of the fixed set from knowing the dimensions of the subgroups. So the convention, the Borel formula. And then in the 70s, Petrie showed that for general smooth actions on spheres, there is no such formula. You cannot predict the dimension of the fixed set from knowing the dimension of the fixed sets of proper subgroups. Most dramatically, there are actions with 1 fixed point on the sphere, smooth actions with 1 fixed point, which are sort of drastically different from representation spheres, which will always have at least 2 fixed points, the north and south pole. Okay, so those are background facts on this. And then about rank 2 finite groups themselves, this is a difficult subject, actually. This is really substantial work in the 1950s, and the most recent one for the 2 groups was done by Danko in 2005, so really quite recently. However, there's a complete classification of these things. Well, more or less complete. So here's a sort of a chief actor in this story, this particular group, which is called QDP. I guess it's something to do with quadratic. Anyway, you take ZP cross ZP and you do this semi-direct product. So thinking of ZP cross ZP as just a vector space of rank 2 or over the finite field FP, you can act on it by SL2 FP in the natural way, linear transformations. So
that's a semi-direct product.
It's a semi-direct product. That's right. Yeah. And somehow the key thing about this group is the way the P-CELO subgroups are fused together under the action, the conjugation action. Okay, so there's a fact which is various people have proved. I guess I didn't put a credit here, but if you had a finite GCW complex homotopy equivalent to a sphere, then this group can't participate. There is no, for this QDP group, there is no finite GCW complex with rank 1 isotropy. So if you're going to try to prove something about existence, you better keep track of this exception. The rank 2 finite simple groups are all classified, and the classification is not at all easy, even though you might think that for rank 2, it should be easier than the whole 10,000 pages or whatever it is supposed to come out of the whole program. This part was done much earlier, but it's still not easy. I mean, if somebody asks you, well, I have a rank 2 finite simple group whose 2-CELF subgroup is D8, the dihedral group of order 8. And you ask you, well, what is that group? Well, it turns out to be a PSL2FP. It's I thought at one time I would ask a master's student to go through this and write an exposition of this proof. And it turned out to be I mean, there's impenetrable general arguments, and there's Brouwer's original proof, which is 50 pages of character theory. Anyway, there's a rich and interesting subject here in group theory. I recommend if you ever want to know something about finite simple groups, you should get in touch with Ron Solomon and ask your questions. The books, there are a series of books. The early ones are pretty good on this, but they're, I think, not easy to read. Anyway, for the question that we're really concentrating on, there are lots of examples in this list where they don't have orthogonal representation spheres with rank 1 isotropy. Here are some of the examples. The first one on this list, the symmetric group on 5 letters, is the place where this project started with the work that we did with Semra and Ergun, the first paper that we wrote on this. But there are other interesting groups, as you see in this list. M11, that's one of the Matthew groups, the exceptional simple groups. Okay, here's a little definition. So we want to eliminate all traces of QDP. So essentially, you don't want to have QDP as a subquotient. That's what this says. I think I'll say more about that. So just think QDP is not a subquotient. And if it doesn't, in the sense of that previous definition, essentially, if there's no subquotient, which is a QDP for any odd prime, then we say that the group is QDP free. Use of terminology. Okay, so here's in some way our here's our theorem about setting C, the finite GCW complex setting, the least restrictive setting. So here this looks like, I think, a clean statement in the sense that it's an if and only if condition. All you have to do is eliminate QDP, and you can find a GCW complex homotopy equivalent to a sphere with rank 1 and prime power isotropy. It gets substantially more complicated if you mix the primes in the isotropy subgroups, but we as you will, I hope, see later on, the arguments will produce these examples work 1 prime at a time and then various mixing techniques. So prime power isotropy is an important ingredient. Okay, so you might wonder, well, why shouldn't the talk be over now? The original question has been answered. But it doesn't, so I'll tell you one thing about, I'm going to sketch the proof of a stronger, our answer to part B, I guess I'm going to say. But the thing about this answer is that these finite GCW complexes can have, first of all, the fixed point sets of such a complex will not be spheres in general. There will be homology spheres. That's again Smith theory, that if you look at a P group acting on an N sphere, then the fixed point set is also going to be a ZB homology sphere, not necessarily an actual sphere. So that's already different from orthogonal representations, and but maybe that's not, you don't find that so serious. But the serious thing is that these actions, in order to construct them like this, you have to put in arbitrarily high dimensional cells beyond N. And that's pretty bizarre, right? So and actually this theorem corrects some let's say insufficiencies in the earlier literature about these constructions. So anyway, these kind of examples are pretty far away from manifolds. So we wanted to move on. Okay, so we're going to move on to is the homotopy representations. I already sort of said this, just repeat that that's a finite GCW complex. And there's a dimension function that tells you that fixed point set for every proper subgroup H is homotopy equivalent to a sphere, an actual sphere of some dimension NH. And empty set is dimension -1. Okay, that's what Tom Dieck called a homotopy representation. Oops, did I do that? Right. So Wolfgang Luke developed extensively the sort of theory of transformation groups, particularly in the presence of isotropy, by well, it's actually Tom Deek's introduction of orbit category methods. The orbit category, I guess I'm thinking is familiar to many people in the audience, but it's an easy definition. You take a group and the objects of the category are coset spaces, G mod H, and the morphisms are just G maps between two such coset spaces. So out of this category, you can do modules by taking contrary functors out of this category into R modules where R is any commutative ring, let's say. And once you can do modules, you can do chain complexes, you can do all of sort of algebraic topology over the orbit category. Okay. So this is a point of view that Luke developed in his lecture notes on transformation groups. So there are geometric things, the finite GCW complex, and in a bit we're going to have algebraic things which will model in the orbit category, model the finite GCW complexes. Okay, so I want to sort of gear just this couple of definition to state the main theorem that we proved about the homotopy representations. There are some primes that are interesting. So the primes at which the group is actually rank 2 as opposed to having rank 1. And the families of subgroups and the union of that family. And so here's the sort of the main theorem that we proved. It's published back in 2016. So there are two assumptions here. You need a QDP-free assumption that has to be ruled out, of course. And then there's a condition on character theory, which I don't think I'm going to recall. This is where the difficulties are being buried in the theorem by, well, assumed away, if you like to say this. But anyway, this is I think an interesting condition on finite groups. This two regularity. It has to do with the way that the CELO subgroups are the sort of what's called the fusion system of the finite group. But I didn't want to include this very technical definition in the talk. And then there's a condition that arises from Smith theory. If you take a fixed point set, well, you look at these normalizers, the normalizer in G of H over H, where H is one of these groups in this family HP of rank 1 P subgroups. Okay, so then under those two, so the second condition is a fairly easy consequence of Smith theory. First condition is essential for our arguments, but it is rather complicated condition in group theory, representation theory. However, the outcome is says that we actually produce a finite G homotopy representation with isotropy in the family of subgroups, rank 1 isotropy. Again, P primary isotropy. Okay, so you might, of course, wonder what, particularly with this two regular condition, what applications or what specific groups one could apply this to. So the first example is the example that we did with, Erin and I did with Semra. And this is the group on 5 letters. So if you know and understand this group quite well, I think, you know that it's rank 1 at all the odd primes. Just think about the cycle decomposition. And at the prime 2, you have it's rank 2, dihedral subgroup. So this is an example where you have a single prime where it's not it's a single prime where it's rank 2, and otherwise it's rank 1. And if you feed that into the theorem, then the theorem applies to that, and you get an example, a general example. But S5 was well, the way this started was that the papers on the spaceform problem. So starting with Swan's 1960 paper on periodic projective resolutions. out of a group that has, remember, rank 1, every CELO subgroup is either cyclic or generalized quaternion. Any such finite group, Swan says, I can produce a periodic projective resolution, and actually by splicing a periodic free resolution from Z to Z with exact in the middle. And then you can realize that by a finite free GCW complex. The beginning of the spaceform problem, turning that thing into manifolds is the sort of what the surgery part did, and was eventually solved in the mid-70s, except for the hard algebraic number theory that's left over. But anyway, so what this project started by thinking, well, if you have an action on a sphere, which is GCW sphere, which is rank 1 isotropy, or as a homotopy representation, let's say, then what you should think of is that at every level, for every subgroup, you have a periodic resolution. So over the trivial group, and then over every fixed subgroup, you have shorter and shorter periodic resolutions corresponding to the dimension of the fixed set. If you have if H is a subgroup and you XH is a sphere, homotopy equivalent to a sphere, then that emits an action of NH over H, and then you're going to see some periodic resolutions, sort of layers of periodic. So that's exactly what the orbit category encodes for you, is that algebra, putting it all together. So we produced the first example for this group S5. I think the sphere was dimension 43, something like that. The GCW complex is dimension 43. And the argument has many elements in common with the general theorem, but we introduced some new ideas later on. Okay, so that's a specific case where the theorem applies if you don't have very much rank 2, just a single prime where it's rank 2. And then we investigated the rank 2 finite simple groups. So I'm sure you remember the whole list from some slides ago, but maybe just to say that the whole list is longer than this list. So these are the ones that possibly that emit a finite G homotopy representation with rank 1 isotropy prime power order. So applying our theorem. So we had to work through all of those, that the 2 regular, the fusion conditions and so on, with a lot of help from our friends to understand how these, to understand, you really have to get into the detailed structure of these rank 2 finite simple groups. Okay, there are a few, the earlier ones, unless the PSL2, for example, the PSL2Q, so Q is a prime bigger than or equal to 5. It's, if on an earlier slide, I said that if the prime was bigger than 7, there's no orthogonal representation with rank 1 isotropy. So in this series, in the first few elements, 1 and 2 here, generally above 5 and above 3 for Q in the second example, there's no orthogonal examples. So these are all sort of what you might call new examples. And the last, one of the last 2, I've forgotten which one, does have an orthogonal representation, but we were just trying to list all the finite rank 2 finite simple groups that have this, exhibit this behavior. Okay, well, let's see. So I guess the rest of the talk, I wanted to sort of tell you a bit about the ingredients that go into proving the main result. And the first step is to replace to build an algebraic model. So that's so what is the algebraic model going to be? You have to say what a algebraic homotopy representation is going to be. Where should you start? You could quite generally start with any ring and an R gamma G module. So gamma G is this orbit category, and R gamma G module is a contravariant functor from the orbit category to R modules. Say left R modules or right. So pick a side. That's what R mod is. And mentioned you then can do chain complexes and so on. So an algebraic homotopy representation has a little bit of a complicated internal structure that I'm not going to detail, but you're invited, of course, to read our paper if you're interested in finding out the exact terms. So essentially, it's an R homology n sphere, and I've already sort of said what that is. That you have a dimension function on this. It's a finite projective chain complex, not necessarily a free complex. There's a nice notion. This category has enough projectives to do resolutions. It's a really nice setting for representation theory, more exactly for integral representation theory when you do Z gamma G modules. Anyway, there's some internal conditions, and this is a kind of a messy technical slide, but there's the function that gives you the dimension of the formally gives you a dimension of a fixed set is this so-called superclass function. It just means it's constant on conjugacy classes of subgroups, not just on elements. Okay, so there's an important definition for moving on, which is that you have two sorts of dimensions here. You've got the dimension of the fixed set. Oh yeah, I probably should have said and didn't put on the slide. If I have a GCW complex, how do you get into this setting? You take the, sorry, I can write, maybe right here. If you have this, this is Tom Deeks notation, and this is, if you plug in, it's more compact for the orbit category, just to say the subgroup in the coset G mod H. So the value of this is the functor from the orbit category into chain complexes. And I'm saying a GCW complex that gives you such a functor. And what you do is you simply plug in the chain complex of the fixed set. So that's all you do to get the structure that's involved here. So when you do that, this is one, you have two sorts of dimensions. This is a finite projective chain complex. It started out as finite. It has a dimension over every subgroup. That's dim C at H. And it also, you can take the homology over the orbit category, and every subgroup H, that has a dimension. So that in other words, that the highest dimension where the homology is not zero, that's the homological dimension. So the term tight may not be it's made up for the purpose, but where those two, the homological dimension of your complex and the actual chain complex dimension, in other words, the biggest dimension of cells in that. So if they're the same, that's tight.
When you take homology, or when you say is an homology sphere, are you sort of tensoring with the constant module and taking homology, or you take homology in the
Just look at the
models over the orbit category?
You look at at every subgroup H, you look at the ordinary homology of that. And that, I think maybe did I say something a little bit more? Okay, repeat it a bit here. Yeah, so at every subgroup K, the reduced homology of that is the same as for an NK sphere for every K in your fixed set. Yeah, I probably should have said, because you mentioned this in your talk, that the orbit category has various flavors depending on how you restrict the family of, in the G mod H's, you can restrict the H's to a subfamily of all the subgroups. And that gives you interesting variations of the algebra. Okay, so I hope that's clear for you. So we studied the algebraic question about finite free chain complexes over the orbit category, which are homology n spheres. And the tightness, we proved that if you like to go from this finite free chain complex to an actual finite chain complex, so or up to homotopy equivalent, and that can be done if you have if it's tight, if and only if it's an algebraic homotopy representation. And then this, oops, I keep doing that too many terms. Yes, and then the key to eventually producing the examples is that if you have an algebraic homotopy representation and some about enough stability on the dimensions of the various fixed sets, then you can find a finite GCW complex realizing that over the orbit category. Okay, so somehow that's the goal, is to produce the input for this theorem to produce the examples. Okay. Okay, I think the rest is, if I remember correctly, is going to be an outline for the, so theorem A was the theorem that produces homotopy representations out of that input. And
I missed every NK had to be
greater than or equal to 3.
Great.
So if you grew up on Swan's paper on periodic representations, periodic projective resolutions, you would remember that when he had a free resolution which starts with Z and ends with Z and has free modules over the group ring in the middle, and that's, you know, supposedly like the chain complex of an action on a sphere, of a free action on a sphere. What he does to realize that is to make an argument to say that the first part of it up to dimension, through dimension 2 can be like the skeleton of a KG1. And after that, the chain complex. So once you've identified your chain complex to make it agree with something you actually know geometrically, the KG1 up to the 2 skeleton. After that, and that's essentially an elaboration of Chanuel's lemma, fundamental representation theory thing. Anyway, after you have that, the rest of the chain complex tells you how to add higher cells, and you just work up inductively using the Hurewicz theorem. So that's where that comes in at every level in our argument. Okay, so the goal is to produce equivariant homotopy representations using the assumptions on our group. And the method is going to be to first produce algebraic ones and then use this theorem to realize them geometrically. Okay, so I'm not going to say more about the geometrical realization part, I don't think, but okay, so okay, so there are a number of steps. I'm just going to outline them and maybe not say a whole lot about them in detail, partly because it's a little bit while since I looked at this material and some of this is a little vague in my head. But anyway, let's see how this goes. So the first thing, so this is all the first part is in algebraic models. And we're going to do, first of all, algebraic models at every prime for which the P rank is 2. Okay, so we have to produce these things. Now, the ingredients to this are some work of Jaskowski, McClure, and Oliver, where you get finite dimensional GCW complexes with P group isotropy and whereas FP is cyclic. So if you know something about Bob Oliver's thesis and early work on transformation groups, this is the kind of thing that he was doing. He was producing various sorts of contractible complexes as a model for group actions. But then this is done a later development of that. Okay, so this is not that easy. None of the work we're quoting of other people, none of it's that easy to do, but we're happy they did it. Okay, so suppose you have one of those at a particular prime. The whole first part, just fix a prime where it's have rank 2. Suppose you got one of those. And here's the key step to get down to rank 1 isotropy is this theorem of Jackson. This is Michael Jackson, who this was part of this effort to understand free actions on products of spheres. That Adem and Smith later. So I'm going to make that connection a bit better at the end. But in any case, he did some character theory and produced something called a p-effective character. And that has the property that when you go to fixed sets, you get rank 1 isotropy. Okay, so Adem, Smith, and in fact, an earlier paper of Connolly and Prasidis, out of that, the B that was constructed up there, you can find a GF equivariant spherical fibration, so that E has rank 1 P group isotropy. So the idea of that argument is that you have your space B, which has P group isotropy, but it might not be rank 1 or anything. If it's QDP free, you have this character which allows you to take linear representations. So over a fixed point, what you're going to do is you're going to take a linear representation on a sphere with that isotropy. And that's going to be like a building block for your spherical fibration. So you could perhaps imagine doing this cell by cell and constructing your spherical fibration cell by cell. And you need some compatibility over the boundary of the cells, which has to do with understanding the homotopy groups of the equivariant automorphism groups of spherical spheres and representations. That stuff was done by Schultz, Beck and Schultz. Yeah.
Is this the same B as in Tchaikovsky-McClure? Yeah.
So that's the starting point. So I'm trying to draw a thread between a prime and the ultimate thing. So out of this, so now the progress here is that you do actually have some kind of space, this E, which has it's a spherical fibration over the B, and it has rank 1 P group isotropy. Okay, so now the next part of this is to get the fixed point sets of that H to be actually spheres, and the chain complex of that E to be a finite projective chain complex. But remember, what we're aiming for are finite free chain complexes. So there's a finiteness obstruction problem coming in here, which is going to be solved in the same way as Swan did by splicing. Okay, so some progress is being made. That space E has the right isotropy, and its chain complex is finite projective chain complex over this Z localized at P. We just got to local algebra here. Okay. Yeah. So so as you vary the prime P, the dimension function that occurs for the model at P might be totally different from the dimension function that occurs for another prime Q. The spheres could be actually in different places. So in order to make them the same, you need to find a way of adding and subtracting homology from projective chain complexes to make the dimension functions the same. So that was the next step, modifying the local models to get the same dimension function. Okay, so this this is where that condition, which I said the P.A. Smith condition comes in. And we use the chain complexes over the orbit category to actually do this. So really just a kind of bird's eye view, I think, of the process here. But anyway, the next now you've got a model. Now you've got a model for every prime P where the thing has rank 2, and now we'd like to get something over the integers. Okay. Well, in principle, you know how to do that. It sort of belongs to localization squares. When you compare the integers to localize at P, if things agree over the rationals, you have a chance of putting them together. The local models have the same dimension function, and they have rank 1 P group isotropy at the various P's in S of G. So there could be a bunch of primes where the rank is 2, and you have rank 1 isotropy at those primes. Okay, so the way we build this, the ZG thing, is using a construction over the orbit category due to Dold, which mimics Postnikov towers. So this may be familiar construction. Postnikov towers are familiar construction in homotopy theory. There's a construction in chain complexes which adapts. Dold did it for ordinary. We easily adapted it to the orbit category. So you start in the same way as you do with a Postnikov thing. You start in dimension 0 and you feed something in and take a fiber and add something in dimension 1 and so on. It's a beautiful paper from when 70s, I guess, probably even early 70s. With this. Okay, so this is what's going to get us into the world of the Z gamma G complexes. And the construction that we're doing has to keep this tightness condition that I mentioned, and then we apply the theorem about type being realized by a finite GCW complex. So this is a sort of a detour. I mean, it's a path through a certain process. And maybe the only point I wanted to sort of emphasize about this is working a prime at a time. You have to make the hardest problem is probably constructing the individual prime pieces. Putting them together then uses some new techniques in homological algebra. Yeah, there's a lot of Mackey-Functor stuff in this homological algebra, that these X'd over the orbit category has if one of the parts is X'd into a Mackey-Functor, then the X'd groups have Mackey-Functor structures, and that's used in this. There's, as I recall, an analog of Grimm's theorem about projective modules over the orbit category. Anyway, various elements. I think the last thing I wanted to say about this was, I guess, another motivation for the original project. So the original project, as I said, was understand finite GCW complexes of rank 1 isotropy. So one motivation is, well, because it's there. It's the next step from free actions. Going to allow some isotropy. Let's start with the simplest kind of isotropy, which is rank 1. But another motivation comes from the work of Adem and Smith. Oh, there's a typo on this last slide. Imlies. That's not a lie, though. It's just anyway, it's just a spelling mistake. Anyway, the Adem and Smith produced some examples of free actions on Sn cross Sm. I expect you've heard of this problem, which problem is that if you have a product of spheres of varying dimensions, finite product of spheres, and you'd like to know if you have a finite group acting freely on this product of spheres, say there are, n spheres in this product, n1, n2, and n spheres in this product. And then the counter conjecture is that the rank of the group that's acting freely must be less than or equal to the number of spheres. That's the still unsolved problem. Adem did foundational work on this in homologically trivial cases. There's a nice history of this problem. The rank for 2 spheres, Connor and Heller proved a long time ago that the rank of the group that it was true, that the rank of the group is less or equal to 2 for 2 spheres. But now what about existence? If you have a finite group of rank 2, can you produce an action on a product of 2 spheres, Sn cross? And you're allowed to have them on unequal dimensions, which is critical for the Adem-Smith constructions. So in there, that's an Annals paper in 2001, and they produced several different techniques. One of their techniques for constructing these actions was to start with a finite GCW complex with rank 1 isotropy and construct a spherical fibration over it, very much in the style of Connolly and Persidis that I tried to describe a few minutes ago. And the total space of that spherical fibration is, after, again, maybe some stabilization, the total space is actually homotopy equivalent to the product of 2 spheres. So when I say a G action on some Sn, that's a GCW complex homotopy equivalent to Sn cross Sm. They're not doing manifold theory here. Anyway, there was a line, there was this that was input for their if they had more examples, they could have produced more on Sn cross Sm. And our work provides a whole lot more examples, which feed into this into that project. Maybe the last thing I maybe wanted to say was that on the question of existence, the sort of the outstanding open problems. Remember QDP. Even Mike remembers QDP. They remember QDP. The outstanding question was how you had to eliminate it from the rank 1 isotropy finite G sub CW complexes, but nobody knows whether QDP can act freely on a product of 2 unequal spheres. It's known that QDP cannot act freely on the product of 2 spheres of the same dimension. But not in general. So people are working on that. If you ask for what groups can act freely on the product of 2 spheres of the same dimension, then I think that's an interesting problem because there are restrictions. QDP can't act, and Bob Oliver in the 80s proved that the alternating group A4 cannot act on a product of two spheres of the same dimension. And that eliminates all of those rank 2 finite simple groups that I put in the list because they all contain A4. That's the reason I mentioned A4 when I produced that list, which, whether or not you remember it, A4 is inside all of those groups. And Oliver, in one stroke, eliminated possibility that any non-abelian finite simple group can act freely on a product of two spheres of the same dimension. And then I got interested in this question with a former postdoc, now faculty member in Bilkent University, Özgün Ünlü, and we produced a number of new existence results for groups acting on product of Sn cross Sn, including the somewhat tantalizing, we thought, tantalizingly close to QDP. The P-Celos subgroup of QDP is what's called the exceptional non-abelian group of order P cubed. So it's an extension of ZP cross ZP by another ZP. It's not split. It is still a rank 2 group in spite of what it looks like. And there were papers in the literature asserting that that group could not act freely on a product of spheres of the same dimension. But in fact, it can, and we proved it. And they can act on sphere S2P-1 cross S2P-1, which is the minimal dimension from cohomological reasons that it can act. And we produced a bunch of other examples, some special examples for 3 groups and so on. Anyway, that's still, the general question there is still somewhat open, and I hope maybe to return to that in the future. The other sort of open end of this is going back to our theorem about homotopy representations. There's this G had to be too regular, this condition on its character theory. So it seemed almost possible to characterize the finite rank 2 groups that have that condition and those that don't, but we couldn't quite do it. So that's, I think, an open issue, which we might perhaps, or somebody might return to. Anyway, that's all I wanted to say about this.